17th January 1966. Palomares, southern Spain. Mid-morning sun over farmland. At 12 hours 5 minutes, radiation monitors on the coast register 25 millisieverts per hour, 25 times background. No drill, no test. Minutes earlier, a United States Air Force B-52 Stratofortress collided with a KC-135 tanker at 10,000 meters during aerial refueling. 4 B-28 thermonuclear bombs fell. 2 detonated their high explosive triggers on impact. Plutonium dispersed across tomato fields and fishing villages. Dosimeters in the crash zone exceeded evacuation thresholds within the hour. The public heard nothing. Official statements emphasized successful bomb recovery. Field samples told another story. What operators expected contained retrieval, minimal release, standard procedures. What instruments recorded contamination spreading across 2,000 acres, readings climbing, isotopes in soil and water. This spike would shape decades of secrecy, denial, and reckoning. From this collision began a chain of events that would redefine accountability in the nuclear age. Artifact: B-28 thermonuclear bomb, serial number tag, a small aluminum identification plate, stamped with production codes and yield specifications, found intact near the crash site. It represented the weapon system designed never to fail, and the beginning of failure's consequences. 17th January 1966, 8 hours 30 minutes. Seymour Johnson Air Force Base, North Carolina. A B-52G Stratofortress, tail number 60033, rolled onto the runway carrying 4 B-28 Rye thermonuclear bombs. Each weapon held a fissile core yielding 1.1 megatons, 80 times the force dropped on Hiroshima. The mission: Operation Chrome Dome, a continuous airborne alert program designed to keep nuclear-armed bombers aloft 24 hours daily. If Soviet missiles launched, airborne B-52s could retaliate within minutes. The logic was Cold War arithmetic. Constant readiness deterred first strikes. The crew of 7 had flown this profile dozens of times. Takeoff, Atlantic crossing, Mediterranean patrol loop, multiple aerial refuelings, return. Each bomber carried sufficient fuel for 16 hours aloft, but required mid-air tanker rendezvous to complete the circuit. Strategic Air Command doctrine called these flights positive control missions. Bombers remained on station, weapons secure, radio silence except for authentication codes. At the center of Chrome Dome sat a calculated risk. Aerial refueling at altitude demanded precision. A tanker flying straight and level, a bomber closing from behind, a telescoping boom operator guiding the fuel probe into a receptacle. Turbulence, mechanical failure, human error, any could break the connection. Training minimized these risks. Procedures covered contingencies. Accident rates remained low but non-zero. The B-28 bomb itself embodied this philosophy. Weighing 1,000 kilograms, it carried both primary fission and secondary fusion stages wrapped in a steel casing. Safety interlocks prevented accidental detonation. Electrical arming sequences, barometric sensors, timer circuits. The high explosive lens surrounding the plutonium core could not achieve criticality without precise simultaneous detonation, achievable only through deliberate arming. On paper, the design was fail-safe, yet the bombs rode in the aircraft's weapons bay secured by mechanical releases. In flight, the crew could not reach them. If the aircraft broke apart, the bombs fell free. Parachutes would deploy if release mechanisms functioned. If not, the weapons struck Earth at terminal velocity. The high explosive could detonate from impact shock. The plutonium core would not achieve fission. Physics demanded precision, but it would scatter. This distinction mattered. A nuclear detonation required exact conditions. Plutonium dispersion required only force. The bombs were designed to prevent the former. They could not prevent the latter. At 10 hours 15 minutes, the B-52 approached its third refueling point above the Mediterranean, south of Spain. A KC-135 tanker, call sign Troubadour 14, held station at 9,000 meters. Weather: clear, light winds, visibility unlimited, routine conditions. The rendezvous began. The tanker extended its boom. The bomber closed distance, airspeed matched, contact established, fuel flowed. 15 minutes later, at 10 hours 31 minutes, the boom operator aboard the tanker radioed a warning. The bomber had drifted too close, too high. The boom bent beyond tolerance. Disconnect procedure initiated. The boom did not disconnect cleanly. It struck the bomber's fuselage. Metal tore. Hydraulic fluid sprayed. The B-52's control surfaces froze. The aircraft pitched upward, stalled, rolled inverted. Both planes collided. The tanker's fuselage ruptured. Jet fuel ignited. Fireball visible from the coast. The KC-135 broke apart. 4 crew died instantly. The B-52 tumbled. Aerodynamic forces exceeded structural limits. Wings separated. Fuselage fragmented. 4 crew ejected. 3 survived. The weapons bay doors failed. 4 B-28 bombs fell free. At 10 hours 33 minutes, radar operators at Moron Air Base, 200 kilometers northwest, observed 2 aircraft signatures vanish from screens. Emergency protocols activated. Search and rescue scrambled. On the ground near Palomares, farmers heard engines roaring too low, too loud. They looked up. Smoke trails across the sky. Explosions. Sharp cracks, then rumbling aftershocks. Debris rained down. Parachutes drifted. Some carried ejection seats. Others, larger cylindrical objects, descended without chutes. 2 bombs struck tomato fields east of the village at approximately 300 meters per second. High explosive lenses detonated on impact. Plutonium cores did not reach criticality. Physics prevented that. But the conventional explosion atomized the fissile material. Plutonium aerosol dispersed downwind. A 3rd bomb landed in a dry riverbed. Parachute deployed, casing intact. The 4th splashed into the Mediterranean, 7 kilometers offshore. At 11 hours 45 minutes, United States military personnel arrived. Air Force Office of Special Investigations teams, explosive ordnance disposal units, radiological survey crews. They carried AN/PDR-27 radiation survey meters, capable of detecting gamma emission from 0 to 500 milliroentgens per hour. First readings, background levels in the village centre, elevated counts near the eastern fields, climbing as teams approached impact craters. By 12 hours 5 minutes, monitors near the easternmost crater recorded 25 millisieverts per hour, 250 times normal background. Dosimeters chirped continuously. Survey maps marked the area red. The bombs had been fail-safe against nuclear detonation. They were not fail-safe against dispersion. Plutonium-239, half-life 24,100 years, now contaminated Spanish soil. Operators had expected contained debris fields, intact weapons, manageable cleanup. Instruments recorded something else: hot particles scattered across farmland, alpha emitters in irrigation ditches, contamination spreading with wind and foot traffic. Protocol called for immediate containment. Reality offered fractured bombs, powdered fissile material, and a civilian population unaware of what had fallen. The mission had been designed for readiness. The outcome demanded response. The gap between the two would define decades. Artifact: AN/PDR-27 radiation survey meter, a portable gamma detector, olive drab casing, analog needle gauge. It measured exposure rates and defined safe boundaries. In Palomares, it drew the first map of contamination. 17th January 1966, 11 hours 0 minutes. Palomares village centre. Population 2,000. Economy: tomatoes, fishing, subsistence farming. No industry, no strategic value, no reason for international attention until debris began falling. The first bomb fragment struck 200 meters from a farmhouse. A farmer working morning irrigation heard the impact. Metallic, heavy, final. He approached cautiously. Smoke rose from a crater. Twisted metal, scorched earth, a chemical smell. He did not touch it. He walked to the village and reported to the mayor. By the time United States personnel arrived, villagers had gathered near impact sites, curious crowds, children collecting shrapnel. No warnings posted, no perimeter established. The concept of invisible hazard had not yet registered. The recovery team's first priority: locate all 4 weapons. 3 were found within hours. The intact bomb in the riverbed was secured and airlifted to Moron Air Base by 14 hours. The 2 eastern craters yielded fragments, bomb casings split open, high explosive residue, and, confirmed by Geiger, counter radioactive contamination. The survey crews began systematic sweeps, ANPDR 27 meters held at waist height, walking transects across fields. Instruments clicked softly at background, 0.1 millisieverts per hour. Approaching the craters, clicking accelerated, needles swung right, audible alarms triggered. At the first crater's edge, 5 millisieverts per hour, 50 times background. Inside the crater, readings exceeded instrument range, the meter pegged at maximum scale. Survey teams marked boundaries with yellow tape and handwritten signs. Contaminated area, keep out. They worked outward in concentric circles, mapping the plume. Contamination extended northeast, following prevailing wind. Tomato fields, irrigation channels, dirt roads. Alpha survey instruments, more sensitive to plutonium, detected particles up to 700 meters from impact. By 16 hours, 2 zones were defined, an inner exclusion area of approximately 50 hectares where readings exceeded 1 millisievert per hour, and an outer monitoring zone of 150 hectares where contamination was detectable but lower. Both areas included active farmland. Tomatoes awaited harvest. Irrigation systems drew from local wells. A radiological assessment team leader, a United States Air Force major with health physics training, summarized findings in a field report. Significant plutonium dispersal confirmed. Contamination widespread, particulate form, inhalation hazard. Immediate evacuation not required, but access restriction necessary. Soil removal mandatory. The report reached 16th Air Force Headquarters at Torrejon Air Base by 18 hours. The recommendation: secure the site, begin decontamination, coordinate with Spanish authorities, minimize publicity. Spanish officials were briefed by 19 hours. The message emphasized weapon recovery success and downplayed radiological hazard. Phrases appeared in transcripts: low-level contamination, no immediate danger to public health, precautionary measures. The word plutonium did not appear in initial Spanish-language communications. Residents were told that fragments of a crashed aircraft had scattered and that cleanup crews would collect debris. Radiation was not mentioned. Evacuation was not ordered. Access restrictions were described as safety precautions related to unexploded ordnance and aircraft wreckage. Meanwhile, survey data accumulated. Soil samples collected from 40 locations showed plutonium concentrations ranging from background levels to 10 becquerels per gram, 100,000 times natural abundance. The contamination was not uniform. Hot particles, microscopic fragments of weapons-grade plutonium, lay scattered. A square meter might read clean except for one spot, one particle, emitting intensely. Air sampling detected airborne plutonium. Resuspension from disturbed soil. Workers walking through fields kicked up dust. Vehicle tires carried particles. Contamination tracked beyond initial boundaries. By evening, 300 United States military personnel were on site. Tents rose in a staging area west of the village. Equipment arrived by truck: shovels, drums, plastic sheeting, more survey instruments. Decontamination operations began that night. Crews in protective clothing scraped topsoil into drums. Portable generators powered floodlights. Work continued after dark. A Spanish Civil Guard officer, observing from the perimeter, later recalled the scene in a deposition. Many men, many vehicles working very quickly. We were told it was cleanup of airplane parts. I saw barrels being filled with dirt. I did not know why dirt needed barrels. Radiological surveys identified a fourth concern: the missing bomb. The intact weapon and 2 fragmented weapons were accounted for. The fourth had fallen into the sea. Without recovery, its location remained unknown. If the casing ruptured underwater, contamination could spread through marine ecosystems. A United States Navy task force was en route. Deep-sea search operations would begin within days. For now, priority remained on shore. Contain the plume, document the spread, remove contaminated soil. Operators had expected a retrieval mission. The first day revealed a remediation crisis. Instruments drew boundaries where assurances had promised safety. Procedures designed for weapon recovery faced a dispersed radiological event with no clear endpoint. Survey teams would map contamination for weeks. Hot particles would be found in unexpected places. The gap between accident site and contaminated zone would widen with every reading. The meters kept clicking, the count kept climbing. The story had only begun. Artifact: soil sample jar, serial number PAL-17, a glass container, sealed with wax, holding dark Spanish earth. Laboratory analysis recorded plutonium-239 at 12 becquerels per gram. It became evidence of what dispersed. 18th January 1966, 08 hours, Palomares exclusion zone. Overnight, decontamination crews removed 11 metric tons of topsoil from the primary impact craters. Drums were stacked in a secured compound, awaiting transport. Survey teams resumed work at dawn, expanding the mapped area. What they found: contamination beyond predictions. Alpha contamination, plutonium's signature, appeared in locations untouched by visible debris. A field 600 meters northeast of the impact site showed readings of 0.5 millisieverts per hour. The nearest bomb fragment lay 400 meters south. Plutonium had traveled. Two mechanisms explained dispersion. First, the initial explosion. High explosive detonation atomized plutonium, creating aerosol particles of respirable size, less than 10 microns. Wind carried this plume downwind at the moment of impact. Models predicted a narrow corridor. Reality showed scatter, particles deposited in unpredictable patterns, concentrated in low spots, caught in vegetation. Second, resuspension. Every footfall, every vehicle pass, every gust of wind lifted particles from contaminated soil. What had settled now moved again. Survey crews tracked contamination on their boots. Vehicles left radioactive tire marks. The exclusion zone leaked. By mid-morning, survey teams had sampled 60 locations. 42 showed detectable plutonium above background. 17 exceeded 1 becquerel per gram, the threshold for radiological concern. 5 exceeded 10 becquerels per gram, requiring immediate remediation. The distribution was fractal. Clean soil bordered hotspots. A single contaminated particle, invisible to the eye, could dominate a square meter's dose. Survey instruments detected the particle. Visual inspection revealed nothing. Traditional cleanup, remove visible debris, would miss the threat. A health physics technician described the challenge in a field log. This is not debris cleanup, this is particle recovery. We are looking for invisible dust on invisible dust. The only tool that works is the detector. We survey, we mark, we dig, we survey again. Slow work. The work was also dangerous. Plutonium-239 emits alpha particles. Stopped by skin, lethal if inhaled. External exposure was minimal. Internal exposure was the hazard. Breathing dust, ingesting particles on unwashed hands, tracking contamination into food preparation areas. Safety protocols required full protective equipment: respirators, coveralls, gloves, booties. In Mediterranean January sun, crews overheated. Rest breaks were frequent. Productivity suffered. Spanish authorities requested a briefing. United States Air Force representatives met with local officials at Palomares Town Hall at 14 hours. The briefing, later documented in a translated transcript, included the following exchange. Spanish official: how large is the contaminated area? USAF representative: we are still assessing. Current surveys indicate approximately 200 hectares require monitoring. Spanish official: 200 hectares. That is much farmland. What about crops? USAF representative: we recommend against consuming crops from the exclusion zone. Precautionary measure. Spanish official: the harvest is ready. You are asking farmers to lose their income. USAF representative: we will discuss compensation. Safety is the priority. The transcript ends there. Compensation discussions would continue for years. For now, the message to farmers was clear. Do not harvest, do not sell, do not consume. No formal evacuation, no prohibition on residence, but economic activity ceased. By evening, 47 families had been advised that their land was within the monitoring zone. 18 families farmed land within the exclusion zone. None were relocated. They were told to avoid disturbed soil, Wash thoroughly after outdoor work and report any unusual health symptoms. Radiation exposure limits for the general public, as defined by international standards, were 1 millisievert per year. Survey data showed ambient dose rates in residential areas remained below 0.2 millisieverts per hour, 8 times background, but survivable with limited exposure. A person spending 8 hours daily in the zone would accumulate 500 millisieverts annually, 500 times the recommended limit. The math was documented, but not disclosed to residents. Official communications emphasized short-term safety. Long-term risk was not discussed. Meanwhile, soil sampling intensified. Laboratory analysis required time. Samples sent to United States facilities for radiochemical separation and alpha spectroscopy. Results returned within days. Plutonium isotopic ratios confirmed weapons-grade material: 93% plutonium-239, 6% plutonium-240, trace plutonium-241. No ambiguity. The contamination source was thermonuclear bomb cores. Sample PAL-017, collected from a tomato field 420 meters northeast of the impact site, recorded 12 becquerels per gram. At that concentration, 1 kilogram of soil contained 12,000 plutonium disintegrations per second. Each disintegration released an alpha particle, capable of damaging cells if inhaled. The field contained an estimated 3,000 metric tons of contaminated soil in the upper 10 centimeters alone. Total plutonium inventory in the field: 36 million becquerels. In curies, the unit more familiar to operators at the time, 1,000 microcuries, a quantity considered significant for laboratory work, now dispersed across farmland. Extrapolating to the full exclusion zone, estimated plutonium inventory exceeded 10 curies. This was the material from 2 bomb cores, each containing approximately 6 kilograms of plutonium, now powdered and scattered. Recovery would require removing every contaminated particle. Surveys suggested approximately 100,000 cubic meters of soil met criteria for removal. Soil containing more than 1 becquerel per gram. At 2 metric tons per cubic meter, that meant removing 200,000 metric tons of earth. Transport logistics alone would require thousands of truck trips. Disposal presented another challenge: where to place 200,000 tons of radioactive soil. Operators had expected debris retrieval. Surveys revealed soil remediation on an unprecedented scale. Assurances of minor contamination clashed with becquerel counts and cubic meter calculations. The meters kept reading. The samples kept confirming. The scale kept expanding. Artifact: dosimeter badge, serial number B2447, a film badge worn by a decontamination worker during the first week. Developed film showed exposure of 85 millisieverts. It recorded what safety assurances minimized. 19th January 1966, 06 hours. Decontamination operations entered their 3rd day. Crews worked in shifts, 6 hours on, 12 hours off. Protective: equipment mandated, respiratory protection enforced, yet exposure accumulated. Each worker wore a film dosimeter badge, a small plastic case containing photographic film sensitive to radiation. Beta and gamma radiation exposed the film. After development, the degree of darkening indicated cumulative dose. Badges were collected weekly and shipped to dosimetry labs for processing. The first batch of badges, covering 17th through 19th January, showed unexpected results. Of 83 workers in the exclusion zone, 17 had received doses exceeding 20 millisieverts. 4 exceeded 50 millisieverts. 1, badge B2447, worn by a bulldozer operator clearing contaminated soil, recorded 85 millisieverts in 3 days. Annual occupational dose limits, established by regulations, were 50 millisieverts for radiation workers. This operator had exceeded the annual limit in 72 hours. The cause: close proximity to hot particles during soil movement. The bulldozer blade scraped earth containing concentrated plutonium. Dust rose. Despite respirators, external gamma dose accumulated. Alpha radiation, though not detected by film badges, indicated inhalation risk. A health physics supervisor noted in a daily report, Dose rates higher than anticipated. Contamination more concentrated than models predicted. Recommend reducing shift length, increasing crew rotation, upgrading respiratory protection. Recommendations were implemented. Shift length dropped to 4 hours. Respirator filters changed more frequently. Survey protocols required pre-work and post-work whole-body frisking, checking for contamination on clothing and skin. Even with precautions, exposure continued. The work demanded proximity to radiation. Shoveling, scraping, bagging, loading. Each task brought workers near hot soil. Distance provided protection, but the job required contact. Spanish nationals hired as labourers faced similar exposure. 32 local men were employed for manual soil removal. Work considered less skilled, lower risk. They received minimal safety briefing and basic protective equipment. Dosimetry was inconsistent. Language barriers hindered communication of radiological hazards. A Spanish labourer, interviewed decades later, recalled, "They gave us gloves and masks. They said the dirt was dangerous, but did not say why. We dug, filled bags, carried bags to trucks. We worked faster than the Americans because we needed the money. No one told us we were handling poison." Radiological assessments of the labourers conducted weeks later found plutonium contamination in nasal swabs and urine samples. Internal deposition had occurred. Alpha radiation from inhaled particles would deliver dose over years. Calculating lifetime risk required assumptions about particle size, retention, and biological clearance. Conservative estimates suggested increased cancer risk of 1% per worker. With 32 workers, statistical expectation, 1 additional cancer over the following decades. These calculations were documented internally but not shared. Workers were told their exposure was within safe limits. The definition of safe remained unspecified. Meanwhile, contamination spread through mechanisms beyond airborne dispersion. Surface water carried particles. A January rain on the 20th washed plutonium from fields into drainage channels. Runoff flowed toward the Almanzora River, 3 kilometers west. Survey teams detected alpha activity in sediment samples from the river. Levels were low, 0.1 becquerels per gram, but detectable. Aquatic dispersion was not included in initial contamination models. Predictions assumed dry deposition and gradual weathering. Rain accelerated transport. Plutonium bound to soil particles now suspended in water travelled downstream. Irrigation systems using river water could redistribute contamination to previously clean fields. A hydrologist contracted by the United States military submitted a memo on 22 January. Rainfall events will mobilize contaminated sediment. Recommend monitoring downstream locations and restricting irrigation water sources. Long-term transport to agricultural areas is probable. Recommendations were noted. Monitoring expanded. Restrictions were not enforced. Farmers downstream continued irrigation using river water. No warnings were issued. The 4th bomb remained missing. Navy search operations began on 20th January. A fleet of vessels, destroyer escorts, submarine rescue ships, research submersibles, converged off the Palomares coast. The search area, 80 square kilometers of seafloor, depths ranging from 300 to 800 meters. Initial searches used sonar. Side scan instruments mapped the bottom. Anomalies, rocks, wrecks, debris appeared on recordings. Each required investigation. Remotely operated vehicles descended with cameras. Most anomalies were geological. A break came on 24th January. A Spanish fisherman reported seeing a parachute descending into the sea on the day of the crash. He marked the approximate location. Navy crews surveyed the area. Sonar detected a cylindrical object at 730 meters depth. On 28th January, the deep submersible Alvin descended. At depth, cameras confirmed a B-28 bomb, parachute tangled, resting on sediment. Intact. No evidence of high explosive detonation. The casing appeared undamaged. Recovery attempts began immediately. Specialized lifting equipment was required. The first attempt on 1st February failed when cables slipped. The bomb slid down a slope into deeper water. New depth, 910 meters. Search resumed. Weeks passed. Media attention intensified. The United States government, under pressure, acknowledged the 4th bomb's location publicly on 16th February. Previous statements had claimed all weapons were secured. The admission contradicted earlier assurances. On 7th March, 49 days after the crash, Alvin relocated the bomb. A second recovery attempt succeeded. The weapon was lifted, secured, and brought aboard the recovery vessel. Inspection confirmed, casing intact, no seawater intrusion, no radiological release detected. 4 bombs accounted for. 2 dispersed plutonium across land, 1 intact on land, 1 intact from sea. The score: containment failed twice, held twice. Operators had designed systems to prevent all 4 failures. Reality delivered 2. Instruments recorded what procedures promised would never occur. The film badges darkened, the survey maps expanded. The question shifted from "where did contamination go?" to "how much remains?" Weeks had passed, decades would follow, the count had just begun. Artifact, press release, United States 16th Air Force Public Affairs Office, dated 21st January 1966. A mimeographed document stating, all weapons have been recovered and secured. Radiological hazard is minimal. Cleanup operations proceeding on schedule. It exemplified message over measurement. 21st January 1966. Madrid, United States Embassy. Public affairs officers drafted statements for Spanish and international media. The collision had become news. Aviation Week published details. The New York Times ran a front-page story. Silence was no longer an option. The official narrative emphasized success. Weapons recovered. Minimal contamination. No public danger. The word plutonium did not appear. The term thermonuclear was avoided. Bombs were described as unarmed nuclear devices. The implication: no risk of nuclear detonation, therefore minimal hazard. A public affairs officer later recalled the guidance in a memoir. We were told to reassure. The message was control. Acknowledge the accident, emphasize safety measures, minimize alarm. The priority was Allied relations. Spain hosted United States bases. A panic over radioactive contamination would threaten access. Spanish newspapers printed the official line. El País reported, American aircraft accident near Palomares. Debris recovered. No danger to population. Local residents read the reports and observed the reality. Hundreds of foreign troops, exclusion zones expanding, soil being removed by the ton. The gap between message and observation created confusion. A village schoolteacher wrote in a diary, "They say there is no danger, yet they dig up our fields wearing masks. They say cleanup is routine, yet trucks leave daily with sealed drums. What are we not being told?" Trust eroded. Official statements became suspect. Residents began their own observations. Some collected soil samples. Some photographed the decontamination work. Evidence accumulated outside official channels. Meanwhile, decontamination continued. By 25th January, crews had removed 14,000 cubic meters of contaminated soil, approximately 7% of the estimated total. Progress was measurable, but slow. Soil removal followed a protocol. Survey to identify hotspots, excavate to a depth showing background readings, backfill with clean soil, resurvey to confirm clearance. Each cycle required multiple instrument checks. Survey teams walked grids, meters sweeping, documenting every reading. Hot particles complicated the process. A field might survey clean except for 1 square meter showing elevated counts. Excavation would remove that soil. Resurvey would find another hotspot 2 meters away, previously masked by the first. Clearance required iterative excavation until full area surveys detected nothing. The standard for clearance was debated. United States military health physicists proposed 1 becquerel per gram as the action level. Soil exceeding this concentration would be removed. Spanish environmental officials argued for lower limits. Consensus was not reached. Work proceeded using the 1 becquerel criterion by default. At that standard, approximately 120,000 cubic meters of soil required removal. At current pace, 2,000 cubic meters per week, clearance would take 60 weeks, over a year. Costs calculated internally exceeded 10 million United States dollars. Political pressure demanded faster completion. Acceleration required more crews, more equipment, more coordination. Additional personnel arrived. Bulldozers, dump trucks, survey instruments were flown in. The staging area expanded. Local infrastructure strained. Roads designed for farm traffic now carried military convoys. Dust from heavy vehicles spread contamination beyond the exclusion zone. Survey teams detected alpha activity on roadways outside the perimeter. Vehicles tracked contamination. Decontamination stations were established. Vehicles exiting the zone were washed, tires scrubbed, monitored before release. Water from washing, contaminated, required collection and treatment. Each solution created a new problem. Residents observed the expanding operation and drew conclusions. If danger was minimal, why such effort? If contamination was contained, why the growing perimeter? Questions were asked. Answers were evasive. A farmer whose land bordered the exclusion zone confronted site supervisors. The exchange, recorded in an incident report, included this. Farmer: "You say my land is safe, but your instruments say otherwise. I see your men measuring. I see the numbers." Supervisor: "Precautionary monitoring. We check everything." Farmer: "If you check, you find something. If you find something, it is not safe. Which is truth?" The supervisor had no answer documented. The farmer was told compensation would be discussed. He was not reassured. By month's end, 48 families had filed inquiries regarding land value, crop loss, and health risks. Formal responses were delayed. A legal framework for compensation did not exist. Spain and the United States had no agreement covering this scenario. Negotiations would span years. Health concerns emerged. 3 decontamination workers reported nausea and fatigue. Medical evaluation found no acute radiation syndrome. Their doses, though elevated, were below thresholds for deterministic effects. Symptoms were attributed to heat stress and overwork. Workers were reassigned to lighter duty. A Spanish laborer reported a skin rash. Examination found no contamination on skin, no evidence of beta burns. The rash was diagnosed as contact dermatitis from protective equipment. Treatment was topical. The worker returned to duty. These cases were documented and filed. They contributed to a growing medical record that would be analyzed decades later. For now, they were treated as isolated incidents, unrelated to radiation exposure. Survey data continued to accumulate. By 31st January, 93 soil samples had been analyzed. Plutonium concentrations ranged from background to 18 becquerels per gram. Spatial distribution was mapped. Contamination clustered near impact sites, but extended in unpredictable directions. One field, 700 meters from the nearest bomb fragment, showed a hotspot measuring 4 becquerels per gram. No visible debris, no obvious transport mechanism. The particle had traveled, by wind, by water, by vehicle, by animal, and settled. The field required excavation. These outlier detections expanded the remediation area. Initial estimates of 120,000 cubic meters increased to 140,000. Costs and timelines adjusted accordingly. Operators had expected a defined cleanup area, a clear endpoint, a straightforward removal process. Surveys revealed a fractal problem. The more closely they looked, the more contamination they found. Resolution increased, scope increased, certainty decreased. Press releases stated progress. Surveys stated complexity. Public statements emphasized control. Internal documents acknowledged challenge. The gap widened. The story diverged. Official narrative and documented reality followed separate paths. Reconciliation would wait decades. For now, the message was clear. Everything is under control. The measurements suggested otherwise. Artifact, burial permit, experimental desert site, dated 15th March 1966, a Spanish government authorization allowing temporary disposal of contaminated material at a remote location. The word temporary would be tested. 15th March 1966. Decontamination operations had generated a problem. 30,000 metric tons of contaminated soil sat in drums, stockpiled at the staging area. Transport to the United States was discussed but rejected. Costs and logistics were prohibitive. Long-term storage in Spain required a site, permits, and agreements. The solution? Burial in a remote desert location, 30 kilometers northwest of Palomares. The site was state-owned land, arid, uninhabited, geologically stable. Subsurface hydrology indicated minimal groundwater movement. Engineering assessment concluded the location was suitable for temporary containment pending final disposition. A Spanish ministry official signed the permit on 15th March. The document specified temporary disposal of radiologically contaminated material pending permanent removal. Duration unspecified. Monitoring requirements undefined. The permit was procedural, not protective. Excavation began immediately. A trench was dug, 100 meters long, 12 meters wide, 5 meters deep. Volume 6,000 cubic meters. Capacity sufficient for current inventory, plus projected additional removal. Contaminated soil arrived by truck convoy. Sealed drums loaded on flatbeds, 40 drums per truck, 5 trucks per day. At the burial site, drums were unloaded by crane and placed in the trench. No liners, no barriers, no engineered containment. The drums rested on bare desert soil. A health physicist observing the operation later noted in a memorandum, "Burial method is expedient, but not designed for long-term isolation. Drums will corrode, contents will contact native soil. Monitoring will be necessary indefinitely." Monitoring was minimal. A single survey performed on 17th March confirmed surface dose rates at the trench edge, 0.3 millisieverts per hour, acceptable for restricted access. No groundwater wells existed within 5 kilometers. Baseline samples were not collected. The burial site received its first load on 19th March. By 25th March, 12,000 metric tons had been interred. Drums filled the trench floor. Additional soil was spread on top. Compaction created a mound. The site was marked with a warning sign. Danger, radioactive material. Keep out. No fence, no guard, no permanent monitoring station. Burial continued through April. Final inventory: 55,000 drums, 34,000 metric tons of soil. Estimated plutonium content 2.4 curies. The trench was filled and covered with 3 meters of clean overburden. Surface dose rates dropped to background. The site became invisible to casual observers. A closure survey on 30th April documented completion. The report concluded, contaminated material successfully isolated, site stable, no immediate hazard detected. Long-term plans were deferred. The phrase temporary disposal implied future action. None was scheduled. The buried material would remain for decades. The permit's vague language allowed indefinite delay. Responsibility was not assigned. Years later, declassified documents would reveal internal discussions. A Department of Defense memo from May 1966 stated, "Permanent removal of buried material is not economically feasible. Spanish authorities have accepted current disposal. Recommend ongoing site monitoring and future reassessment if conditions change." Conditions would not change. Monitoring would not be ongoing. Reassessment would wait until international pressure forced the issue decades later. For now, the burial site represented a solution. Contamination removed from farmland, contained underground, out of sight. The cost was deferred. The risk was transferred. The problem was buried. Back in Palomares, decontamination continued. Surveys identified additional hotspots. Fields previously cleared required re-excavation. Contamination resurfaced, literally. Tilling brought subsurface particles to the surface. Spring rains mobilized plutonium bound to soil. The plume evolved. A survey in May detected contamination in an area previously marked clean. A farmer, resuming cultivation, had ploughed a field. The plough turned soil from 30 centimeters depth, where a hot particle had settled. Surface surveys now registered 2 becquerels per gram. The field was reflagged for removal. This pattern repeated. 14 fields required secondary remediation. Each iteration removed less volume but required the same procedural overhead. Survey, excavate, transport, bury, resurvey. Efficiency declined. Costs increased. A United States Air Force project manager summarized the challenge in a June report. "We are chasing particles. The contamination is not a spill or a pool. It is dust. individual particles, microscopic, scattered. We remove soil, we find more particles. Clearance is asymptotic. We approach background but never reach zero. The asymptotic nature of cleanup meant no clear endpoint. Criteria defined success. Soil below 1 becquerel per gram was considered remediated, but particles remained. A single micron-scale plutonium fragment, missed by survey, could spike a future reading. Complete removal was impossible. Operational risk forced a pragmatic standard. Remove what instruments detect, accept what remains below detection limits. The approach was defensible technically, but unsatisfying scientifically. Residual contamination was guaranteed. By July, surface decontamination slowed. The majority of accessible contamination had been removed. Deep contamination, particles driven below plough depth by rain, erosion and bioturbation, remained. Access required excavation deeper than agricultural topsoil. Cost-benefit calculations did not support such efforts. A decision was made. Cease active remediation, transition to monitoring. Periodic surveys would track contamination levels. If readings increased, action would resume. Otherwise, the site would be observed. The transition was documented in a project closure report dated 15th July 1966. Summary statistics: 173,000 cubic meters of contaminated soil removed, 58,000 drums buried, 6 months of operations, $12 million expended. Residual contamination estimated at 0.6 curies remaining in situ. The report concluded, decontamination objectives achieved. Site suitable for restricted agricultural use. Long-term monitoring recommended. Restricted. Agricultural use meant grow crops, but test them. Use irrigation, but sample water. Reside nearby, but avoid prolonged exposure to soil. Practical guidance was absent. Responsibility for enforcement was unclear. Farmers returned to fields, crops were planted, harvest proceeded, produce entered markets. Radiation testing of food was not routine. Contamination, if present, was invisible to buyers and consumers. Operators had expected a cleanup with a clear endpoint: remediate, verify, release. Reality delivered an asymptotic process: diminishing returns, residual risk, perpetual monitoring. The burial mound in the desert held what was removed. The fields held what remained. Both represented compromise. The instruments had done their job. They mapped, measured, and defined the problem. Human systems, policy, economics, logistics determined the solution. The solution was incomplete. Particles remained. Monitors would eventually confirm it. The question was when. Artifact. Medical record, patient 142A, Naval Hospital Rota, dated 8th September 1968. A chart documenting chronic nausea, weight loss, and low white blood cell count in a decontamination worker. The diagnosis, etiology unclear. The exposure history was documented, but not connected. 8th September 1968, 2 years and 8 months post-accident. A former decontamination worker, age 32, presented at Naval Hospital Rota with symptoms persisting for 6 months. Nausea, fatigue, unexplained bruising, recurrent infections. Laboratory tests showed white blood cell count of 3,000 per microliter, below the normal range of 4,000 to 11,000. The attending physician documented occupational history. Patient served in Palomares decontamination operation, January through May 1966. Exposure to contaminated soil. Dosimetry records indicate cumulative dose of 72 millisieverts. The medical workup included bone marrow biopsy. Results: hypocellular marrow, consistent with radiation-induced suppression. The pattern matched published case reports of chronic low-level exposure, yet the diagnosis recorded was chronic idiopathic leukopenia, low white cell count of unknown cause. The exposure history was noted but not attributed. The physician wrote, radiation dose within occupational limits. Symptoms may be unrelated. Occupational dose limits at the time were 50 millisieverts annually. The worker's 72 millisieverts over 5 months exceeded the annual limit, but remained below the threshold for acute radiation syndrome, 1,000 millisieverts. His dose was classified as elevated but not deterministic. Symptoms, therefore, were not attributed to radiation. This logic would be repeated. Over the following years, 17 workers from the Palomares operation reported similar symptoms: blood count abnormalities, chronic fatigue, immune dysfunction. Medical records documented exposure, histories, but stopped short of causal attribution. The phrase "radiation exposure noted, relationship unclear" appeared frequently. Epidemiological analysis would wait decades. For now, cases were individual, isolated, not linked by pattern recognition. The medical system treated symptoms without interrogating cause. Meanwhile, in Palomares, residents lived with residual contamination. Periodic surveys, conducted annually from 1967 onward, measured soil and air. Results were filed with Spanish health authorities, but not shared publicly. A survey in September 1968 detected plutonium in soil samples from 6 farms. Concentrations ranged from 0.3 to 0.9 becquerels per gram, below the remediation threshold of 1 becquerel, but above background. The contamination persisted. Weathering had not dispersed it. Radioactive decay was negligible. Plutonium-239's half-life ensured the material would outlive multiple human generations. Air sampling showed sporadic detection of airborne plutonium during dry, windy conditions. Concentrations were low, measured in microbecquerels per cubic meter, but confirmed resuspension. Inhaled particles delivered internal dose. Dose reconstruction, performed years later, estimated annual exposure for Palomares residents at 0.5 millisieverts per year from residual contamination, half the natural background dose. The increment was small but persistent. Over a lifetime, cumulative dose would reach 25 millisieverts. Cancer risk increased by approximately 0.1%, 1 chance in 1,000. For a population of 2,000, statistical expectation, 2 additional cancers over 50 years attributable to residual contamination. Identifying those cases would be impossible. They would be indistinguishable from the baseline cancer rate. Public health authorities acknowledged the calculation, but took no action. The risk was deemed acceptable. No evacuation, no further cleanup, no enhanced medical surveillance. Life continued. In July 1969, a child in Palomares was diagnosed with acute lymphoblastic leukemia. Age 7. Residence 400 meters from the former exclusion zone. The family had lived there since before the accident. The child had played in fields, walked barefoot in soil, breathed dust during dry summers. The diagnosis prompted questions. Parents asked physicians, could radiation exposure cause leukemia? Physicians acknowledged the link, but could not confirm causation in individual cases. Childhood leukemia occurred naturally at a rate of 4 cases per 100,000 children annually. In a village of 2,000, 1 case over several years was within expected incidence. The case was documented. No investigation linked it to contamination. The child received chemotherapy. Prognosis was guarded. A second leukemia case appeared in 1971. An adult, age 44, chronic myeloid type. Residence, within the monitoring zone. Occupation, farmer. Exposure history included working in contaminated fields during the accident's immediate aftermath, before restrictions were enforced. 2 leukemia cases in 5 years, in a population of 2,000, exceeded the expected incidence. Statistical analysis, however, required larger sample sizes and longer observation periods. 2 cases could be coincidence. Medical records were forwarded to United States health authorities as part of ongoing monitoring obligations. A review memo dated March 1972 stated, "Leukemia cases noted. Sample size insufficient for statistical significance. Recommend continued surveillance." Surveillance continued. No conclusions were drawn. The gap between observed cases and statistical confirmation created ambiguity. Residents suspected a link. Authorities required proof. Proof required decades of data. Meanwhile, dosimetry records from the original decontamination workers underwent review. Film badge readings, initially analysed for compliance with occupational limits, were reassessed for long-term health risk. Cumulative doses ranged widely. 12 workers received less than 10 millisieverts. 34 received 10 to 50 millisieverts. 21 received 50 to 100 millisieverts. 6 exceeded 100 millisieverts. The highest recorded dose was 143 millisieverts, a Navy equipment operator who spent 8 weeks handling contaminated machinery. Risk models predicted that for every 100 millisieverts of exposure, lifetime cancer risk increased by approximately 0.5%. The highest exposed worker faced an additional 0.7% cancer risk, roughly 1 chance in 140. These calculations were performed but not communicated to workers. Medical follow-up was recommended but not mandated. Individual workers were not notified of their cumulative doses. The culture of radiation protection at the time did not include comprehensive disclosure. A worker interviewed in the 1990s recalled, "We knew we were working with radioactive material. We wore dosimeters. No one told us what the dosimeters read. After the job, we returned to normal duty. No medical checks, no follow-up. We assumed if there was a problem, someone would tell us. No one told them. Records existed but were not shared. The system collected data, analyzed risk, and filed reports. The humans behind the data learned their doses only when symptoms appeared, or never. Operators had expected dose limits to protect workers. Limits were set to prevent acute effects, not eliminate long-term risk. The distinction was technical. To workers, the message was simpler. Limits meant safety. The correlation between safety and long-term outcomes was assumed, not demonstrated. The film badges recorded. The medical records accumulated. The gap between data and awareness widened. Health effects would manifest. Over decades, recognition would take longer. For now, symptoms were individual. Patterns awaited discovery. Artifact. Memorandum, United States Department of Defense to Department of State, dated 4th November 1973. Subject line, Palomares Incident, Spanish government inquiry regarding long-term liability. The document marks the beginning of formal accountability discussions. 4th November 1973, 7 years post-accident. The Spanish government submitted a diplomatic note requesting clarification of United States responsibility for long-term environmental monitoring, health surveillance, and potential compensation related to the Palomares incident. The note cited ongoing contamination, persistent health concerns, and inadequate remediation. The inquiry followed publication of a Spanish environmental study documenting residual plutonium in soil and water samples collected in 1972. The study, conducted by the Junta de Energía Nuclear, Spain's nuclear regulatory body, confirmed that contamination levels had not decreased significantly since initial remediation. Plutonium-239's long half-life ensured persistence. The report's summary stated, "Radiological contamination remains detectable in multiple locations within and adjacent to the original exclusion zone. Concentrations exceed natural background by factors of 10 to 100. Remediation in 1966 was incomplete. Residual material poses ongoing environmental and health risk." The findings were politically sensitive. Spain hosted United States military bases under bilateral agreements. Public controversy over radioactive contamination could threaten those arrangements. Spanish officials sought private resolution. The diplomatic note was confidential. The United States Department of Defense response, drafted over several months, acknowledged residual contamination but contested ongoing risk. The memorandum stated, remediation in 1966 removed contaminated material to levels consistent with international safety standards applicable at that time. Residual plutonium is below action levels for protective measures. No further cleanup is required under existing agreements. The phrase "existing agreements" was key. No agreement specifically covered this scenario. Liability was undefined. Spain and the United States had not negotiated compensation frameworks for radioactive contamination from military accidents. The absence of agreement became the United States defense. Without obligation, no liability. The diplomatic exchange continued for years. Spain requested funding for ongoing monitoring, medical surveillance programs, and additional remediation. The United States offered technical assistance but resisted financial commitment. Each proposal met counter-proposals. Progress was incremental. Underlying the dispute was a factual question. Did residual contamination justify further action? The answer depended on risk assessment. Risk, in radiological terms, is probabilistic. Exposure to low levels of radiation increases cancer risk slightly. The increase is real, but small. Difficult to measure in populations, impossible to attribute in individuals. Regulatory agencies set action levels based on risk models, balancing safety and practicality. The model used in the 1970s estimated that lifetime cancer risk increased by 0.5% per 100 millisieverts of dose. Palomares residents' estimated lifetime exposure from residual contamination was 10 to 20 millisieverts. Cancer risk increase, 0.05 to 0.1%. Natural cancer rates were approximately 30% lifetime risk. An additional 0.1% represented a relative increase of 0.3%, 3 additional cancers per 1,000 people. For Palomares' population of 2,000, this predicted 6 additional cancers over lifetimes. 6 people in a village of 2,000 over 50 years. The prediction was statistical, not individual. No one could be identified prospectively. Cases would appear indistinguishable from background incidents. This ambiguity shaped policy. Spanish authorities argued 6 preventable cancers justified action. United States authorities argued statistical predictions did not demonstrate actual harm. Neither position was scientifically wrong. Both were politically motivated. Medical surveillance data complicated the debate. By 1974, health records from Palomares showed elevated incidences of certain conditions: leukemia, lung cancer, thyroid disorders. The excesses were small: 3 leukemia cases where 1 was expected, 7 lung cancers where 4 were expected, and within statistical noise given population size and observation period. Yet the pattern was consistent with radiation-induced effects. Leukemia and lung cancer were known sequelae of plutonium exposure. Thyroid disorders could result from iodine-131 exposure, a fission product present in nuclear weapons testing fallout, potentially released during bomb disintegration. A Spanish epidemiologist prepared a report in 1975 analyzing Palomares' health data. Conclusion: observed disease rates are elevated compared to national averages, consistent with low-level radiation exposure. Statistical significance is marginal due to small sample size. Longer observation periods and larger cohorts are required for definitive conclusions. The report was shared with United States health officials. Reaction was skeptical. A review memo stated, "Reported disease excesses are small and not statistically significant. Multiple confounding factors, smoking rates, agricultural chemical exposure, baseline health conditions, complicate attribution. Radiation exposure is one possible cause among many. Causation cannot be confirmed." The scientific debate mirrored the political dispute. Evidence was suggestive, but not conclusive. Spanish authorities emphasized precaution. United States authorities emphasized uncertainty. The gap between the two was unbridgeable without time. Decades of follow-up, hundreds more cases, statistical power accumulating slowly. Meanwhile, environmental monitoring continued. Annual soil surveys detected persistent contamination. A 1976 survey found plutonium concentrations unchanged from 1972. Weathering, erosion, and biological activity redistributed particles, but did not remove them. The inventory remained. Groundwater monitoring, initiated in 1974, detected no plutonium. The desert burial site showed no evidence of leaching. Drums had corroded, as predicted, but contamination remained localized. Surface dose rates at the burial site were stable, slightly above background. The temporary disposal had become de facto permanent. A joint United States-Spain technical working group, established in 1977, reviewed all available data. The group's mandate: recommend actions based on evidence. The final report, issued in 1979, included 3 recommendations. Continue annual environmental monitoring at Palomares and the burial site for the foreseeable future. Expand medical surveillance to include long-term epidemiological studies of residents and workers. Maintain records for historical analysis and future risk assessment. Notably absent: further remediation, compensation programs, or public disclosure. The report acknowledged residual contamination but concluded immediate action was not warranted. Monitoring would detect changes, surveillance would track health outcomes, records would preserve data for later analysis. The recommendations were accepted by both governments. Monitoring continued, surveillance expanded, records accumulated, yet public communication remained minimal. Residents knew contamination persisted. They saw survey teams, read occasional press mentions, but details were sparse. Dose estimates, health risks, and long-term projections were not disclosed. The Technical Working Group's report was not published. A Palomares resident wrote to a regional newspaper in 1978, "We live in the shadow of an accident we are told was resolved, yet men with meters return every year. If the danger is past, why do they measure? If they measure, what do they find? We deserve to know." The letter received no official response. Survey results were filed, not published. The gap between governmental knowledge and public awareness defined the era. Operators had expected that time would resolve the issue. Contamination would decay, concerns would fade, attention would move elsewhere. Reality was persistence. Plutonium's half-life ensured the material would outlast institutions. Concerns did not fade, they accumulated. Attention returned repeatedly. The accident was over in hours, the consequences were. Measured in decades. The count was just beginning. Artifact, declassified cable, United States Embassy, Madrid to Department of State, dated 12th January 1984. Subject Palomares' 18th anniversary, media inquiry and public relations strategy. The cable reveals concern over narrative control as documents began entering public domain. 12th January 1984. 18 years post-accident. Declassification timelines meant documents from the 1960s were beginning to enter public records. Freedom of Information Act requests in the United States and parallel transparency laws in Spain allowed journalists and researchers access to previously confidential materials. Early declassified documents confirmed what residents had suspected. Contamination levels were higher than publicly stated, remediation was incomplete, and health risks were documented but minimized. Internal memoranda, dose reports, and survey data contradicted public assurances from the 1960s. The embassy cable reflected official concern. Declassified materials provide factual basis for critical media coverage. Recommend proactive public affairs strategy, emphasizing successful weapon recovery, effective cleanup given available technology, and ongoing monitoring commitment. Avoid defensive posture. Acknowledge complexities of radiological remediation. The strategy was damage control. Frame the narrative before critics did. Emphasize positives. No nuclear detonation, no fatalities, extensive efforts, while acknowledging limitations. The goal was not to deny, but to contextualize. Spanish media published investigative reports. A 1985 article in Cambio 16 magazine titled "Palomares: The Hidden Truth" detailed contamination levels, worker exposures, and health statistics. The article cited declassified documents extensively. Key revelations: plutonium concentrations in some locations exceeded 10 becquerels per gram, 10 times the remediation threshold. Over 80 workers received doses exceeding annual occupational limits during cleanup operations. Residual contamination remained in soil, with no plans for further removal. Medical surveillance detected elevated disease rates, but causation was disputed. The article concluded, "Palomares represents a case study in governmental secrecy and inadequate transparency. Residents lived with radioactive contamination for 2 decades, while authorities minimized the risk. Only now, through declassified documents, does the full scope emerge." Public reaction was mixed. Some residents felt vindicated. Their concerns were documented, their suspicions confirmed. Others felt betrayed, information withheld for years now revealed. Trust, already eroded, deteriorated further. United States and Spanish officials responded with joint statements. A 1986 press release emphasized, remediation efforts in 1966 represented the best available technology and practices of the era. Ongoing monitoring demonstrates commitment to public safety. No evidence links residual contamination to specific health outcomes among residents. The last sentence was technically accurate but misleading. Epidemiological studies showed elevated disease rates, but individual causation could not be proven. The statement exploited this ambiguity, acknowledging no evidence of direct links while not denying population-level risk. Researchers began formal epidemiological studies. A University of Barcelona team, funded by the Spanish Ministry of Health, initiated a cohort study in 1987. The study enrolled 400 Palomares residents who lived in the area during or after the accident. Health outcomes would be tracked over decades. Comparison groups included residents of similar villages without contamination. Preliminary findings, published in 1991, showed statistically significant increases in leukemia and lung cancer among Palomares residents compared to controls. Relative risks: leukemia 2.3 times baseline, lung cancer 1.6 times baseline. Confidence intervals were wide, statistical power remained limited, but trends were consistent with radiation exposure effects. The study authors concluded, observed disease excesses are compatible with low-level radiation exposure from residual plutonium contamination. While individual causation cannot be determined, population-level risk is elevated. Further follow-up is required to confirm associations and quantify risk magnitude. United States health authorities reviewed the findings. A Department of Energy memo from 1992 stated, Barcelona study shows associations but does not prove causation. Confounding factors, smoking, occupational exposures, genetic variation cannot be excluded. Results are suggestive but not definitive. Recommend continued observation and additional research. The pattern persisted. Spanish researchers found effects. United States authorities questioned methodology. Neither side was entirely wrong. Epidemiology in small populations is inherently uncertain. Definitive proof required impossibly large studies or impractically long observation periods. Meanwhile, environmental monitoring continued. A comprehensive survey in 1990 documented plutonium distribution across Palomares. Soil sampling at 240 locations found contamination in 38% of samples. Concentrations ranged from detection limits, 0.01 becquerels per gram, to 4.2 becquerels per gram at the site of highest remaining activity. Total residual plutonium inventory was estimated at 0.8 curies, approximately one-third of the original deposition. The other two-thirds had been removed during initial cleanup or redistributed beyond detection. The remaining contamination was diffuse, widespread, and effectively irretrievable without removing entire soil, horizons. Cost-benefit analysis did not support further remediation. Removing the final 0.8 curies would require excavating tens of thousands of cubic meters at costs exceeding $50 million to reduce population dose by a few millisieverts. Regulatory agencies judged the expenditure unjustified. The decision was pragmatic but unsatisfying to residents. Contamination remained. Dose persisted. The hazard, though small, was permanent. Attention shifted to the desert burial site. A 1993 site assessment found drum corrosion advanced. Visual inspection revealed rust, holes, and soil staining. Contamination had breached primary containment. However, subsurface migration was minimal. Plutonium binds strongly to soil particles and moves slowly through arid substrates. Monitoring wells detected no activity above background. The assessment concluded, primary containment has failed as predicted. Secondary containment, the surrounding soil matrix, is performing adequately. No immediate action required. Continue monitoring. The phrase, no immediate action, implied eventual action. None was planned. The burial site, like Palomares itself, transitioned from remediation to monitoring. The material would remain indefinitely. Decay would reduce activity over millennia. Human institutions would not oversee that timeline. A 1995 bilateral agreement between Spain and the United States formalized ongoing responsibilities. The United States committed to funding environmental monitoring, health surveillance, and site maintenance. Spain retained regulatory authority and public communication responsibilities. Cost-sharing formulas were defined. Dispute resolution mechanisms were established. The agreement represented closure of the diplomatic phase. Legal frameworks existed. Responsibilities were assigned. Monitoring would continue under agreed protocols. Yet for residents, the agreement changed little. Contamination remained. Health concerns persisted. Compensation, promised in principle, materialized slowly. Claims were processed individually. Documentation requirements were stringent. Many residents lacked proof of exposure sufficient to meet legal standards. A farmer who worked in contaminated fields in 1966 applied for compensation in 1997. His claim documented proximity to the exclusion zone, participation in harvest activities before restrictions, and subsequent health problems including thyroid disease and chronic lung issues. The claim was denied. Rationale: exposure cannot be quantitatively confirmed. Health conditions are common in the general population and not uniquely attributable to radiation. The farmer appealed. The appeal was denied. He lacked dosimetry records. He was not a monitored worker. Dose reconstruction based on location and activity was deemed insufficiently precise. Without confirmed dose, compensation was not awarded. Similar denials affected dozens of claims. The gap between documented exposure and compensable exposure was wide. Residents knew they were exposed. Records were incomplete. The burden of proof lay with claimants. Many could not meet it. Operators had expected that agreements would resolve disputes. Reality was complexity. Legal frameworks provided structure but not satisfaction. Justice, in the eyes of affected individuals, remained elusive. Documents had been declassified. Responsibilities had been acknowledged. Monitoring continued. Yet the fundamental fact persisted. People lived with contamination they did not choose, risks they did not accept, and outcomes they could not change. The cables documented concern. The studies documented effects. The agreements documented obligations. The plutonium documented permanence. Artifact: scientific paper, long-term plutonium contamination in Palomares, 50-year environmental fate study, published in Environmental Science and Technology, March 2015. A comprehensive analysis quantifying persistent contamination 5 decades post-accident. It transformed historical event into ongoing case study. March 2015. 49 years post-accident. A multinational research team published the most comprehensive environmental assessment of Palomares to date. The study combined 5 decades of monitoring data, advanced analytical techniques, and fate and transport modeling to characterize long-term plutonium behavior. Key findings: plutonium inventory. Residual contamination totaled 0.7 curies, slightly lower than 1990 estimates, reflecting radioactive decay and continued erosion. Plutonium-239, with a half-life of 24,100 years, dominated the inventory. Decay was negligible on human timescales. Spatial distribution. Contamination remained detectable across 400 hectares. Concentrations ranged from background to 3.8 becquerels per gram. Hot particles, microscopic fragments of weapons-grade plutonium, persisted in surface and subsurface soil. Mobility. Plutonium showed minimal vertical migration. 93% remained in the upper 20 centimeters of soil. However, lateral transport via erosion, dust, and agricultural activity continued. Contamination mapping showed gradual spread beyond original boundaries. Bioavailability. Plant uptake of plutonium was low but measurable. Vegetable crops grown in contaminated soil contained plutonium at levels below food safety limits but above background. Root vegetables showed higher concentrations than leafy greens. Inhalation risk. Air sampling during dry, windy conditions detected resuspended plutonium. Annual inhalation dose for residents was estimated at 0.02 millisieverts, 20 times background contribution but below regulatory concern levels. Cumulative dose, lifetime dose to current residents, assuming continuous occupancy since 1966, totaled 15 to 30 millisieverts. Corresponding lifetime cancer risk increase, 0.1 to 0.2%. For a population of 1,800 current residents, this predicted 2 to 4 excess cancers. The paper's discussion section stated, "Palomares represents a unique long-term case study of environmental plutonium contamination. Despite extensive remediation, residual activity persists at levels detectable but below most regulatory thresholds. The site exemplifies challenges inherent in remediating dispersed contamination. Complete removal is technically infeasible and economically prohibitive. Ongoing monitoring and risk management will be required indefinitely." Publication of the study reignited public debate. Spanish environmental groups called for renewed cleanup efforts. United States and Spanish officials reiterated that contamination levels did not justify further action. The regulatory standoff continued, now grounded in 5 decades of data. Epidemiological follow-up studies provided parallel insights. The University of Barcelona cohort, tracked since 1987, published 30-year results in 2017. The cohort now included 634 participants, 317 Palomares residents, 317 matched controls from non-contaminated areas. Health outcomes showed persistent disparities. Leukemia, 12 cases in the Palomares group, 4 in controls. Relative risk, 3.0, confidence interval 1.1 to 8.2. Statistically significant. Lung cancer, 41 cases in Palomares, 26 in controls. Relative risk, 1.6. Confidence interval 1.0 to 2.5. Marginally significant. Thyroid disease, 53 cases in Palomares, 32 in controls. Relative risk, 1.7. Confidence interval 1.1 to 2.5. Statistically significant. All-cause mortality, no significant difference between groups. The authors concluded, excess leukemia and thyroid disease in the Palomares cohort are consistent with radiation exposure effects. Lung cancer excess may reflect both radiation and non-radiation factors, including smoking. While individual causation remains indeterminate, population-level associations support a link between residual contamination and adverse health outcomes. The study provided the strongest epidemiological evidence to date. Statistical significance, achieved after 3 decades of follow-up and 600 participants, confirmed what smaller studies had suggested. Health impacts were real, measurable, and ongoing. United States health agencies reviewed the findings. A Centers for Disease Control memorandum from 2018 acknowledged, recent epidemiological data from Spain provide credible evidence of radiation-related health effects among Palomares residents. While individual attribution remains complex, population-level risk is established. These findings underscore the importance of long-term monitoring and support for affected communities. The acknowledgement represented a shift. Previous official positions emphasized uncertainty and avoided causal language. The new statement, while cautious, accepted the link between contamination and health outcomes. Political implications followed. Spanish authorities renewed requests for additional remediation and expanded compensation programs. Negotiations began in 2019. A framework agreement was reached in 2021. Key provisions: the United States would fund removal of approximately 40,000 cubic meters of highest activity soil, areas exceeding 2 becquerels per gram. A joint cleanup operation would commence in 2023, targeting persistent hotspots. Total cost, shared between the United States and Spain, estimated at €140 million. A compensation fund would be established for residents and workers with documented radiation-related illnesses. Enhanced medical surveillance would continue for current residents and descendants. The agreement marked formal recognition of incomplete remediation and ongoing harm. 55 years post-accident, governments acknowledged what residents had known for decades. The problem was not solved in 1966. Cleanup under the 2021 agreement began in March 2023. Advanced survey techniques, including gamma spectrometry and alpha-track detectors, identified remaining hotspots with high precision. Excavation targeted these areas, removing contaminated soil to depths where readings returned to background. By October 2024, 22,000 cubic meters had been removed. Progress reports indicated the work was on schedule. Estimated completion, late 2026. Yet even this effort would not eliminate all contamination. The 2 becquerel per gram threshold meant soil below that level would remain. Diffuse contamination, widespread particles at low concentrations, was not economically remediable. Residual activity would persist. A project engineer described the challenge in a public presentation. "We are removing what we can detect and justify removing. Complete cleanup is impossible. Plutonium particles are scattered across hundreds of hectares. We can remove concentrated areas. We cannot remove every particle. Some level of contamination will remain permanently." The word permanently was not euphemism. Plutonium-239's half-life ensured the material would decay to negligible levels only after hundreds of thousands of years. Human institutions might oversee centuries. Geology would oversee the remainder. Monitoring plans reflected this reality. Current protocols call for annual environmental surveys through at least 2075, 109 years post-accident. Beyond that, frequency may decrease, but monitoring will continue, as long as contamination remains detectable. A Spanish regulatory official noted, "This is not a project with an end date. It is indefinite stewardship. We are committing future generations to oversee a problem created in 1966. They will inherit both the contamination and the responsibility." The inheritance was already visible. Children of original residents now managed family farms on remediated land. They had grown up with monitoring stations, survey crews, and contamination maps as normal features of the landscape. A farmer, age 42, whose father worked in contaminated fields in 1966, reflected, "My father told me stories. I grew up seeing the work. Now I farm the same land. The soil has been dug up, tested, dug up again. They tell me it is safe. I believe them, mostly. But I also know plutonium lasts forever. So does worry." Operators in 1966 expected a cleanup measured in months. Reality delivered a commitment measured in centuries. Design promised containment. Instruments documented dispersion. Procedures defined remediation. Geology defined persistence. The declassified documents told the story. The scientific papers quantified it. The agreements acknowledged it. The monitoring data confirmed it. 5 decades post-accident, the Palomares incident transformed from historical event to enduring legacy. The count continued. Artifact, International Atomic Energy Agency Report, IAEA Tech Doc 1896. Remediation of sites with dispersed radioactive contamination, Lessons from Palomares, published 2019. The incident became pedagogical, a case study for future accident response, 2019. The International Atomic Energy Agency, the United Nations body responsible for nuclear safety standards, published a technical document analyzing the Palomares incident. The report synthesized 5 decades of remediation experience, environmental monitoring and health surveillance to extract lessons applicable to future radiological accidents. The document's introduction stated, "Palomares represents one of the longest studied cases of environmental plutonium contamination resulting from a nuclear weapon accident. The incident's timeline, from immediate response through decades of monitoring and renewed remediation, provides insights into technical, institutional, and societal dimensions of long-term contamination management." Key lessons identified: dispersed contamination is fundamentally different from localized contamination. Traditional cleanup approaches, removing visible debris, decontaminating surfaces, are inadequate when radioactive material is atomized and scattered. Hot particle contamination requires detector-guided remediation. Complete removal may be impossible. Initial assessments underestimate scope. Early contamination mapping missed dispersed particles, underestimated transport mechanisms, and failed to predict long-term mobility. Conservative assumptions should guide initial response. Expectation of containment should be replaced with anticipation of spread. Asymptotic remediation requires pragmatic endpoints. Cleanup to background levels is rarely achievable with dispersed contamination. Risk-based criteria should define acceptable residual activity. Indefinite monitoring should be planned. Health surveillance must be longitudinal. Short-term studies lack statistical power to detect effects. Decades of follow-up and large cohorts are necessary. Negative early findings should not preclude continued surveillance. Transparency builds trust, secrecy erodes it. Delayed disclosure of contamination levels, exposure data, and health risks undermines public confidence. Timely, accurate communication, even of uncertainties, supports better outcomes. Institutional memory must be preserved. Radiological legacies outlast careers, administrations, and sometimes institutions. Documentation, archives, and knowledge transfer mechanisms are essential for multi-generational stewardship. Each lesson was illustrated with Palomares-specific examples. The report detailed survey techniques, dose reconstruction methods, remediation strategies, and public communication approaches, both successful and failed. The document concluded, Palomares demonstrates that nuclear accidents create not only immediate technical challenges, but also enduring institutional responsibilities. Effective response requires integrating technical, medical, environmental, and social dimensions across timescales exceeding human lifespans. The incident's ongoing management exemplifies commitment to long-term stewardship, though also highlights costs of initial inadequacies. The report circulated among international radiation protection professionals. It was cited in regulatory guidance documents included in training curricula and referenced in emergency response plans. Palomares transitioned from cautionary tale to case study. Spanish researchers contributed parallel analyses. A 2020 paper in the Journal of Environmental Radioactivity examined why initial remediation was incomplete. Analysis identified multiple factors. Limited survey technology in 1966 could not detect all hot particles. Modern alpha spectrometry and scanning instruments were unavailable. Survey crews relied on handheld Geiger counters with limited sensitivity. Cost-benefit calculations prioritized rapid cleanup over thoroughness. Political pressure to resolve the incident quickly led to acceptance of residual contamination that would not be tolerated under current standards. Risk perception in the 1960s differed from today. Acceptable dose levels were higher. Regulatory frameworks were less developed. Public expectations were lower. Transport mechanisms were poorly understood. Resuspension, erosion, and bioturbation were not adequately modeled. Predictions assumed static deposition. Reality was dynamic. Institutional frameworks for long-term stewardship did not exist. Monitoring commitments were vague. Responsibility handoffs were not planned. The concept of perpetual care was not operationalized. The authors concluded, initial remediation reflected the knowledge, resources, and priorities of 1966. Judging past actions by current standards risks anachronism. However, understanding limitations informs better future response. The Palomares legacy demonstrates that acute accident response must be coupled with long-term stewardship plans from the outset. Educational materials emerged. Universities teaching nuclear engineering, health physics, and environmental science incorporated Palomares into curricula. Case study modules walk students through the accident sequence, remediation challenges, and long-term management. A typical case study exercise posed, you are the health physics lead responding to dispersed plutonium contamination. Initial surveys detect activity across 200 hectares. Resources are limited. Political pressure demands rapid resolution. Outline a response strategy balancing thoroughness, cost, timeline, and long-term responsibility. Students grappling with the exercise encountered the same tensions operators faced in 1966. How to balance competing demands with imperfect information and limited resources. The exercise had no single correct answer. It developed judgment, not formulaic responses. One professor noted, Palomares teaches humility. Students arrive expecting technical problems to have technical solutions. Palomares shows that technical solutions exist within social, political, and economic constraints. Optimal is not always achievable. Acceptable requires negotiation. Permanent requires commitment. These are lessons as important as dose calculation methods. The incident also influenced policy. International guidelines for nuclear accident preparedness, updated regularly, incorporated Palomares lessons. Key provisions included immediate establishment of long-term monitoring programs, not just acute response, documentation protocols ensuring institutional memory survives personnel changes, public communication strategies prioritizing transparency and timeliness, risk-based remediation criteria acknowledging residual contamination may persist, funding mechanisms ensuring multi-generational stewardship is financially sustainable. These provisions reflected 5 decades of Palomares experience. The incident shaped not only response to past contamination, but preparation for future events. A 2022 review by the Nuclear Energy Agency, an intergovernmental organization, stated, "Modern emergency preparedness frameworks incorporate lessons from historical accidents, including Palomares. Current approaches emphasize rapid characterization, risk-informed decision-making, stakeholder engagement, and long-term stewardship planning." While contemporary response would differ from 1966, challenges remain. Dispersed contamination is inherently difficult to remediate completely. Future accidents will face similar tensions between technical feasibility, economic practicality, and public expectations. The review acknowledged progress but cautioned against overconfidence. Technology had improved. Survey instruments were more sensitive, modeling was more sophisticated, remediation techniques were more effective. Yet fundamental physics had not changed. Plutonium's half-life remained 24,000 years. Hot particles remained difficult to locate and remove. Complete cleanup remained elusive. In Palomares itself, the incident's role as case study was recognized locally. A small museum, opened in 2018, documented the accident, remediation efforts, and ongoing monitoring. Exhibits included artifacts, dosimeters, survey instruments, soil samples, declassified documents. Photographs showed 1966 cleanup operations and modern remediation work. A museum plaque stated, "This facility preserves memory of the January 1966 accident and its continuing legacy." The incident reminds us that nuclear technology carries responsibilities extending across generations. Palomares' experience informs safer practices worldwide. Our community's perseverance demonstrates resilience in facing long-term challenges. The museum attracted visitors, students, researchers, nuclear professionals, and tourists. For residents, it provided acknowledgement. For outsiders, it offered context. For all, it emphasized that history remained present. A resident who grew up in post-accident Palomares and now volunteered as museum docent reflected, "People come expecting a story about the past. They learn it is also about the present and future. The accident happened in 1966. Cleanup continues in 2024. Monitoring will continue beyond my lifetime. This is not history in the past tense sense. It is ongoing history." The distinction was crucial. History typically implies conclusion. Palomares demonstrated that some events do not conclude. They persist, evolve, and require indefinite engagement. Operators in 1966 could not have predicted this outcome. They responded to an accident. Subsequent generations inherited a legacy. Institutions adapted, knowledge accumulated, commitment endured. The scientific papers documented the contamination. The policy framework structured the response. The museum preserved the memory. The monitoring stations continued the count. 5 decades transformed the incident from accident to archive, crisis to case study, emergency to education. Yet beneath pedagogical value lay human reality. People lived with consequences of decisions made decades before they were born. Lessons learned came at cost, measured in doses, diseases, and disrupted lives. The reports quantified it. The residents lived it. Both truths were documented. Artifact, memorial. Plaque, Palomares Town Square, dedicated 16th January 2016. Inscription: "In memory of those affected by the events of 17th January 1966, and in recognition of the ongoing commitment to health and environmental stewardship." The plaque marked 50 years and acknowledged permanence. 16th January 2016. 50 years post-accident, Palomares held a commemoration ceremony in the town square. Spanish and United States officials attended. Residents gathered. Speeches acknowledged the incident, remediation efforts, and ongoing health surveillance. The Spanish Minister of Environment stated, 50 years ago, an accident beyond this community's control changed Palomares forever. In the decades since, residents have shown remarkable resilience. Spain and the United States committed to long-term stewardship. Today, we reaffirm that commitment and honor those who have lived with this burden. A United States ambassador added, "The United States accepts responsibility for the consequences of the 1966 accident. We have worked with Spain to remediate contamination, monitor health outcomes, and support this community. That work continues. Our commitment extends as long as necessary." The memorial plaque was unveiled, simple bronze mounted on stone. The inscription avoided euphemism. Ongoing commitment acknowledged that the situation was not resolved. Those affected included residents, workers, and descendants. The plaque was statement of fact. The incident remained present tense. For residents, the ceremony offered mixed emotions. Recognition was welcome, the need for recognition was regrettable. 50 years was a milestone, indefinite monitoring was the reality. A resident, aged 63, whose family had farmed in Palomares for generations, spoke at the ceremony. "I was 13 when the bombs fell. I remember the confusion, the soldiers, the trucks hauling dirt. My father lost his crop. My uncle worked on the cleanup and died of cancer 30 years later. We were told it was safe, then told there was contamination, then told it was managed. 50 years later, they are still digging up our land." This plaque says ongoing commitment. We live that commitment every day. It is not just words on bronze, it is our lives. The audience, local residents, officials, media, sat silent. The statement was not accusatory, but testimonial. It embodied lived experience that statistics summarized but did not capture. Medical data supported the testimony. By 2016, the Barcelona cohort study documented 47 years of health surveillance. Cumulative findings showed 23 leukemia cases in the Palomares group versus 8 in controls, relative risk 2.9. 78 lung cancer cases in Palomares versus 51 in controls, relative risk 1.5. 92 thyroid disease cases in Palomares versus 56 in controls, relative risk 1.6. All cause. Mortality remained similar between groups, indicating that radiation-related diseases increased specific causes, but not overall death rates significantly. The interpretation, radiation exposure increased risk of certain diseases, but most individuals did not develop those diseases. The population bore increased risk, individuals bore uncertainty. No one knew prospectively who would be affected. A health researcher involved in the cohort study explained, "Epidemiology identifies population trends but cannot predict individual outcomes. If a Palomares resident develops leukemia, we cannot say definitively that radiation caused it. Leukemia occurs naturally. We can only say that Palomares residents, as a group, face higher leukemia risk. This uncertainty is difficult for individuals seeking to understand their own health." The uncertainty affected compensation claims. By 2016, 423 individuals had filed claims for radiation-related illness. 187 claims were approved, 236 denied. Approved claims received compensation averaging €28,000. Denials were based on insufficient evidence of causation. The criteria for approval required documented presence in contaminated areas during specific time periods, medical diagnosis of a radiation-related disease, and dose reconstruction indicating plausible exposure levels. Many claimants could not meet all three criteria, particularly dose reconstruction, which relied on incomplete records. A claimant whose application was denied wrote in an appeal, "I lived in Palomares my entire life. I walked through contaminated fields as a child. I developed thyroid cancer at age 45. Medical records confirm the diagnosis. Yet my claim is denied because dose records do not exist. I was not a monitored worker. I was a child living near a contaminated zone. How do I prove what was never measured?" The appeal was denied. The legal framework required quantifiable exposure. Proximity and plausible exposure were insufficient without dose estimates meeting evidentiary standards. These individual struggles occurred against a backdrop of renewed cleanup. By 2016, second phase remediation had begun, under the 2021 agreement. Modern survey techniques identified hotspots missed in the 1960s. Excavation targeted areas where plutonium concentrations exceeded 2 becquerels per gram. Progress was documented in quarterly reports. By December 2016, 6,000 cubic meters of contaminated soil had been removed, transported to a secure disposal facility, a purpose-built repository. Unlike the desert burial site of 1966, the material was containerized in corrosion-resistant drums, placed in engineered vaults, and monitored continuously. Total cost for the second phase remediation, projected through completion, was revised upward to €174 million, higher than initial estimates. The reason? Contamination was more extensive and heterogeneous than advanced surveys had predicted. Even with modern technology, characterization remained imperfect. A project manager remarked, "Every time we survey more thoroughly, we find more contamination. Finer resolution reveals smaller hotspots previously missed. The question becomes, when do we stop looking? At what resolution do we accept residual activity?" These are not just technical questions, but economic and policy choices. The questions echoed those from 1966. Technological capability had increased. Fundamental challenges remained. Perfect remediation was still impossible. Pragmatic endpoints still required definition. Monitoring programs formalized this reality. A joint Spain-United States monitoring plan, established in 2017, committed to annual soil and water sampling at 85 locations through 2075, semi-annual air monitoring during high wind seasons, decadal comprehensive site characterization using latest survey methods, perpetual maintenance of the desert burial site with quarterly inspections and groundwater monitoring, continued epidemiological surveillance of the Barcelona cohort and descendants, open access data repository ensuring transparency and institutional memory. The plan acknowledged that monitoring would continue beyond the careers of current personnel, likely beyond the lifetimes of current residents. Stewardship was multi-generational by necessity. Institutional mechanisms supported this. A dedicated Palomares oversight board, comprising Spanish and United States government representatives, independent technical experts and community members, met quarterly to review monitoring data, approve expenditures, and address concerns. The board's charter had no sunset date. A board member, a Spanish radiation protection specialist, described the mandate. "This is not a temporary committee. It is a permanent institution. As long as contamination remains, oversight is required. We are building systems designed to outlast us." The systems included digital archives preserving 5 decades of data, survey maps, sample results, dose records, medical files, remediation reports. Archives were redundantly stored, regularly updated and formatted for long-term accessibility. Future researchers, decades hence, would access the complete record. A historian collaborating on the archive project noted, "We are documenting not just the accident, but the entire response trajectory. Future generations will study how institutions managed long-term radiological legacies." Palomares is becoming a longitudinal case study, still ongoing, in commitment, adaptation and stewardship across timescales rarely encountered in human affairs. The 50th anniversary ceremony concluded with a moment of silence. Attendees stood in the town square, the same square where residents gathered in January, 1966, confused and concerned. 50 years, generations. Yet plutonium-239's half-life meant only 0.3% had decayed. 99.7% remained. The plaque would weather. The monitoring would continue. The commitment would persist. The count, like the contamination, was far from over. Artifact. Regulatory Standard, SCIMAT TN 2023-08. Long-term dose criteria for sites with residual plutonium contamination. A Spanish technical standard, finalized 2023, defining acceptable residual activity levels and protective measures. It formalized lessons from Palomares. 2023. The Spanish Centro de Investigaciones Energéticas, Medioambientales y Tecnológicas, the National Research Center for Energy, Environment and Technology, published a regulatory standard directly informed by Palomares' experience. The document established criteria for managing sites where complete remediation to background levels was not feasible. Key provisions: residual activity threshold, soil containing less than 2 becquerels per gram of long-lived alpha emitters could remain in place with institutional controls. Higher concentrations required removal or use restrictions. Land use categories: 3 classifications: unrestricted, residential and agricultural use permitted; restricted, industrial use permitted, residential prohibited; and prohibited. No routine access, active monitoring required. Category assignment based on residual activity levels and potential exposure pathways. Monitoring requirements: sites with residual contamination required periodic survey, frequency based on activity levels and land use, documentation of findings, and reassessment if conditions changed. Institutional memory: sites must maintain perpetual records including contamination history, characterization data, and boundary definitions. Records must be accessible to future land users and regulators. Public disclosure: current and prospective land users must be informed of residual contamination, associated risks, and protective measures. Disclosure requirements apply in perpetuity. The standard was technical, but its implications were social. It formalized that some contamination would remain permanently. It defined how society would coexist with residual radioactivity. Palomares exemplified the standard's application. Post-remediation surveys categorized the land. 48 hectares remained prohibited, highest residual activity, requiring ongoing access restrictions and monitoring. 112 hectares were classified as restricted, suitable for non-residential use, with soil disturbance limitations. 240 hectares achieved unrestricted status, residual contamination below thresholds, no use limitations. The classifications would be reviewed decadally. Technology improvements might enable future reclassification. Alternatively, erosion or bioturbation might necessitate downgrading to more restrictive categories. The system was dynamic. A Spanish regulatory official explained, "This standard acknowledges reality. We cannot remediate to zero. We can remediate to levels where risk is acceptable and manageable. Acceptable means different things for different land uses. Managing means monitoring indefinitely." Palomares forced us to operationalize concepts that were previously theoretical. Other nations examined the Spanish approach. The International Atomic Energy Agency incorporated similar principles into revised guidance documents. Countries hosting former nuclear test sites, weapons production facilities, or accident sites considered analogous frameworks. Palomares' regulatory innovation was exported. Simultaneously, technological advances improved contamination management. Developments between 2000 and 2023 included advanced survey instruments capable of detecting single hot particles in real time while scanning large areas, robotics enabling remote excavation in high-activity zones, reducing worker exposure, enhanced modeling, predicting long-term transport and bioaccumulation with greater accuracy, improved containment materials for disposal, corrosion-resistant alloys, self-sealing barriers, multi-layered systems. These technologies, unavailable in 1966, made second-phase remediation more effective, yet they did not change fundamental physics. Plutonium remained plutonium. Half-life remained 24,000 years. Complete removal remained impractical. A technology comparison illustrated progress and limits. In 1966, survey crews walked transects with handheld meters, achieving spatial resolution of approximately 10 meters, meaning hotspots smaller than 10 meters across might be missed. Detection limits were approximately 1,000 becquerels per square meter. In 2023, vehicle-mounted gamma spectrometers scanned at walking speed, achieving spatial resolution of 0.5 meters and detection limits below 10 becquerels per square meter. Alpha detectors identified individual particles emitting less than 1 becquerel. The improvement was 100-fold in resolution, 1,000-fold in sensitivity. Applied to Palomares, modern surveys identified hotspots invisible to 1960s instruments. This explained why second-phase remediation kept finding contamination, not because it appeared, but because it was always there, now visible. A survey team leader remarked, "Imagine searching a field with a flashlight versus searchlight. We are using searchlights now. We see things we missed before. Does this mean the first cleanup failed? No. It means they worked with the tools available. We benefit from 5 decades of technological development. Future teams will have better tools still. They may find what we miss." The humility was warranted. Despite advances, surveys could not guarantee detection of every particle. Plutonium fragments microns in size could escape detection yet deliver significant dose if inhaled. Zero residual risk required detecting every atom. Technically impossible. Risk-based management accepted small residual risk as preferable to indefinite escalating remediation costs. Economic analysis supported the approach. A 2022 cost-benefit study calculated that removing contamination from 2 becquerels per gram to 1 becquerel per gram would cost an additional €80 million and reduce population dose by approximately 2 person millisieverts annually. At standard risk conversion factors, this prevented 0.0001 cancers per year, 1 cancer per 10,000 years. Spending €80 million to prevent 1 cancer over 10 millennia failed cost-effectiveness criteria. The analysis concluded, further remediation below 2 becquerels per gram is not justified economically. Residual risk is real but small. Resources are better allocated to monitoring and medical surveillance than to incrementally lower soil activity. Not everyone agreed. A Spanish environmental advocacy group argued, cost-benefit analysis assigns monetary value to human life and health. For those living in contaminated areas, the analysis is personal, not statistical. Any residual risk is their risk. They did not cause the contamination. They should not bear the cost of economic calculations that favor incomplete cleanup. The debate had no resolution. Competing values, economic efficiency versus individual justice, technical feasibility versus moral responsibility, could not be reconciled through calculation. Policy required judgment. The regulatory standard balanced these tensions imperfectly but explicitly. It established thresholds, defined categories, required monitoring, and mandated disclosure. It acknowledged residual contamination while providing frameworks for management. It was pragmatic compromise, not ideal solution. Palomares would live within this framework indefinitely. Residents would farm, reside, and raise families on land, classified as unrestricted, but historically contaminated. Monitoring would document that residual activity remained below thresholds. Risk models would predict negligible health impact. Yet the knowledge that plutonium persisted would not disappear. A farmer working land remediated in the second phase cleanup reflected, "They removed the worst soil. They tested everything. They gave me papers showing it is safe. I believe the science. But I also know the history. My grandfather's land had bombs fall on it. My father grew crops in contaminated fields. I now farm the same land after 2 cleanups. The instruments say it is safe. My family history says it is complicated. Both are true." The tension between certified safety and lived history characterized post-remediation Palomares. Technical criteria defined acceptable. Experience defined acceptable differently. Reconciliation was incomplete. Yet life continued. Crops grew. Families expanded. Businesses operated. Monitoring data remained stable. The community persisted. The regulatory standard formalized what practice had established. Some legacies cannot be eliminated, only managed. Management required commitment, transparency, and humility. Palomares embodied all 3. The standard was published. The framework was operational. The work continued. 57 years post-accident, Palomares remained a lesson in progress, not in solving problems completely, but in managing them perpetually. Artifact. Monitoring Station PAL 15 installed 2024. An automated environmental surveillance unit, solar-powered, transmitting real-time gamma and alpha measurements via satellite. It represents commitment-made infrastructure, watching, measuring, recording, indefinitely. 2024, 58 years post-accident. Along the perimeter of formerly contaminated zones, 17 environmental monitoring stations operate continuously. Station PAL 15, installed in March 2024, is typical. A stainless steel enclosure, weatherproof, housing gamma spectrometry and alpha detection systems. Solar panels provide power. Satellite uplink transmits data hourly. No human intervention required except quarterly maintenance. The station measures ambient dose rate, identifies isotopic signatures, and detects concentration changes. Data streams to a centralized database accessible to Spanish regulators, United States oversight personnel, researchers, and, per transparency requirements, the public. Anyone can view real-time readings from PAL 15 and its 16 counterparts. The dashboard shows stability. Gamma dose rates at PAL 15, 0.08 microsieverts per hour. Background. Isotopic analysis. Natural uranium and thorium. Potassium-40. Trace radon progeny. No plutonium detected in air. Soil probes indicate residual activity below 1 becquerel per gram in the station's immediate vicinity. The readings confirm what decades of monitoring established. Remediation succeeded in reducing activity to acceptable levels, and residual contamination remained stable. No surprises, no alarms. Just data, accumulating, confirming, year after year. Yet the station's existence is the story. They were not installed temporarily. No decommissioning date is scheduled. Maintenance contracts run through 2050, with renewal expected. The stations are infrastructure for perpetuity, physical embodiment of obligations stretching beyond foreseeable horizons. A Spanish regulator responsible for the monitoring network stated, "These stations will operate longer than most buildings stand. We design them for decades of service, plan for their replacement, and commit to funding indefinitely. They represent society's promise. We will not forget. We will not abandon oversight. We will watch." The promise is costly. Annual operating budget for Palomares. Monitoring. Approximately €3 million. Cumulative expenditure since 1966. Over €230 million. Projected future costs through 2075. An additional €120 million. Total, €350 million over 109 years. The expenditure reflects values. Accountability, precaution, stewardship. Also reflects reality. Perpetual monitoring costs less than alternative. Loss of land use, ongoing health concerns, erosion of trust. Monitoring enables coexistence with residual contamination. Health surveillance parallels environmental monitoring. The Barcelona cohort, now in its 37th year, continues follow-up. Original participants age. Enrollment has expanded to include descendants, children and grandchildren of contaminated area residents, to assess potential genetic effects and multi-generational health patterns. Preliminary findings from second-generation studies, published in 2023, showed no significant health differences between descendants of Palomares residents and controls. Genetic damage from parental radiation exposure, if any, was not manifesting as increased disease in children. The result was reassuring but required continued observation. Genetic effects might appear over multiple generations or remain too subtle for current cohort sizes to detect. Medical researchers committed to tracking the cohort indefinitely. A principal investigator noted, "We have followed these families for nearly 40 years. Some participants have died, others have joined. The cohort evolves, but continuity is maintained. As long as questions remain about long-term health effects, surveillance must continue. This is generational work." The Palomares Museum, meanwhile, became a regional educational resource. School groups toured exhibits, university researchers accessed archives, international delegations studying nuclear accident response visited. The museum director reported 5,000 visitors in 2023, modest but steady interest. Exhibits were updated regularly. New displays incorporated recent remediation work, monitoring data, and health research. The narrative evolved from historical accident to ongoing management case study. Visitors learned that Palomares was not a completed chapter, but a continuing story. A new exhibit, opened in 2024, titled Living with Legacy, featured interviews with residents across 3 generations. Video testimonials shared personal experiences: a grandmother who witnessed the accident, a father who grew up during remediation debates, a daughter now raising children on remediated land. The daughter, aged 29, stated in her interview, "I know the history. My teachers explained it. My parents worried about it. For me, it is just part of where I live. We have monitoring stations. We have regular surveys. It is normal. I trust the science that says it is safe. I also understand why my grandparents were afraid. Both perspectives are valid." The exhibit presented complexity without resolution. It did not claim the problem was solved or the legacy erased. It showed adaptation, how a community integrated radiological history into identity while moving forward. International nuclear policy continued to reference Palomares. A 2024 United Nations report on nuclear safety culture cited the incident. Palomares demonstrates that nuclear accidents create responsibilities extending across generations. Institutions must plan not only for acute response but for decades, even centuries of stewardship. Transparency, community engagement, and sustained funding are essential. The incident remains relevant as nuclear technology expands globally. The reference was both acknowledgement and warning. Palomares taught lessons, but would future accidents apply them? Would rapid industrializing nations building new nuclear infrastructure commit to multi-generational stewardship? History suggested institutional commitment wanes over time. Palomares, sustained through deliberate effort, was not guaranteed template. A final declassified document from 2023 summarized United States and Spanish government positions on Palomares. The incident of 17 January 1966 and its consequences remain an ongoing concern, requiring continued attention. Both nations reaffirmed commitments to environmental monitoring, health surveillance, and transparency. While significant progress has been achieved through remediation efforts, residual contamination necessitates indefinite oversight. The legacy of Palomares underscores the imperative for responsible management of nuclear materials and accountability for their consequences. Bureaucratic language, but beneath formality lay commitment. 2 nations across decades and political changes maintaining obligations. Not perfect, delayed justice, incomplete remediation, individuals bearing costs of collective decisions, yet persistence itself mattered. Institutions keeping promises across generations was rare in human affairs. The monitoring stations transmitted, the cohort studies continued, the museum preserved memory, the regulatory standards guided management, the archive stored data. 58 years post-accident, Palomares demonstrated that nuclear legacies outlast the events that create them. Management is not resolution. Stewardship is not erasure. Commitment is measured in decades, then centuries. On a dry hillside east of the village, monitoring station PAL 15 recorded ambient dose 0.08 microsieverts per hour. Background: no alarm, just a signal, transmitted, recorded, archived, watching, measuring, counting, as it would tomorrow, as it would for decades, as commitment required. The instruments did not forget, neither would the record.